This middle section has no video and is about 30 minutes long. Carefully draw the triangle you see on the screen. Generally, when we want to find the area of a plane triangle, the common way is to multiply 1/2 the base times the height. But when the height is not known, there is another way to solve for the area of a triangle using trigonometry. Follow the diagram. Given two sides and the angle of a triangle, the area of the triangle is, in the diagram, area equals 1/2 AB sine of the angle C. Note the alphabetical order, A, B, C, in order to help you memorize this formula. We now prove this fact. Drop a perpendicular from angle B to the base CA and call it H, the height. Focus on the left half of the triangle, and you see that the sine of angle C is equal to H over A. Cross multiply, and you get that H is equal to A sine of angle C. Now substitute this in the basic formula at the top for area of a triangle. A equals 1/2 the base times the height. And you get that the area equals 1/2 B times A sine C. That's how you get the area equal to 1/2 AB sine C. Check out the other ways of working out the formula in the bottom right-hand side and add them to your journal. The study of trigonometric identities is a large topic involving a lot of memory work. I will give you memory aids to help trigger recall along the way to help in memorizing them. Basically, we can say that identities are equalities, where the function on the right side of the equation is identical to the function on the left side of the equation, but they do not look the same. Look at the first entry for reciprocal ratios. For example, the sine of A is identical to 1 divided by the cosecant of A, with a few exceptions where possibly division by 0 might occur. Every identity on this page can be proved by applying analytic trigonometry in the Cartesian plane. For example, sine A equals y divided by r, and 1 over cosecant A is 1 divided by the fraction r over y, which is the same when simplified. So continuing with the rest of the list, cosine A equals 1 over secant A, and tangent of A is equal to 1 over the cotangent of A. You can turn these around too, and use the fact that cosecant of A is equivalent to 1 over the sine of A. Next, I list the special group, which are the tangent of A is equal to the sine of A divided by the cosine of A. The sine of A equals the fraction y over r, and the cosine of A is the fraction x over r. Divide the two fractions and you get y over x, which is equal to the tangent of A. Cotangent A equals cosine of A over the sine of A, and can be proved in the same fundamental way using analytic trigonometry of the Cartesian plane. We go to the next group and we call that the Pythagorean identities, which are very important, and try to commit to memory. Look at the screen. We have that sine squared A plus cos squared A is equal to 1. That's my first equation. The second one is 1 plus cotangent squared A equals cosecant squared A. The third identity is the tangent squared A plus 1 is equal to the secant squared of A. These can be proved again using analytic trigonometry of the Cartesian plane. Let's look at the first entry in my Pythagorean group. If you take sine squared A, you know that it is equal to y over r quantity squared. If you take the cos squared of A and replace it with x plus x divided by r quantity squared, you end up with x squared over r squared plus y squared over r squared. Add them up and it becomes x squared plus y squared divided by r squared. But you know from the Pythagorean theorem that x squared plus y squared equals r squared. So what do you have? R squared divided by r squared is equal to 1, and that is equal to the right-hand side. Now, if you want, you should try on your own to do the same type of proof with equations 2 and 3. Here is another way that you might want to try to solve the identities in the Pythagorean group without using analytic trigonometry. Let's take equation 1. Sine squared A plus cos squared A is equal to 1. What happens if you divide that entire identity with sine squared A? In the first term, sine squared A over sine squared A. That's 1. Cos squared A over sine squared A, why, that's cotangent squared A. And if you have 1 over the sine squared of A, well, that is the cosecant squared A. And that is exactly what you see in the second equation. We will now look at a very important set of identities. This one is called the sum and difference of two angles. I will introduce the statement of the identity and set out a method of proving its truth. The development of the proof is important to the mathematics student, so you should try to reproduce this proof on your own after you have seen how the logic follows line by line to its conclusion. Pause the video and carefully reproduce the diagram. We have the Cartesian plane, and in it we have two angles, POB and BOC. We have dropped two perpendiculars to the x-axis. One is from the point P down to the axis at A, and from the point B down to the axis at C. We also put a perpendicular at the point B to the line PA at D. The angles at the origin are small a and small b. The statement of the identity is that the sine of angle A plus B is equal to the sine of A times the cos of B plus the cos of A times the sine of B. Now, angle BOC is equal angle small a, which equals angle APB. Notice the location of angle APB. You can, if you want to, insert a little a at the angle at P to remind you that that angle is the same size as the angle at the origin. Now, look at the sine of the sum A plus B in the triangle PAO. This triangle contains the sum of the angles A and B. If you take the sine of this angle, it is AP over OP. That is equal to the sum of AD plus PD. You notice that I have broken up the line AP into two parts, AD plus PD. That plus sign is very important, and you will see how it plays a part to be the same plus sign in the top identity where you have sine A plus cos B plus cos A times sine B. Now the triangles OBC and PBD are similar. Therefore, BC is equal to OB sine angle A, and PD is equal to PB cos small angle A. Now, if you substitute in 1 that the sum of the angles A plus B is equal to OB sine A over OP plus PB cos angle A over OP. In triangle OPB, OB over OP equal multiplied by cos B, and PB over OP equals the sine of B. Therefore, by substitution, sine of A plus B is equal to sine little a cos little b plus cos A times sine little b. The best way to memorize this identity is to memorize this as I've written down, sine cap A plus B equals sine cap A cos B plus cos A sine B. The next set of identities are called transformation identities. Look at the screen and follow very carefully. The angles are X and Y. We want to prove the identity that the sine of X plus the sine of Y is equal to 2 times the sine of X plus Y divided by 2 times the cosine of X minus Y divided by 2. We write down in our proof the following identities and we add them. First, sine A plus B, remember you studied those in the last set of identities, and sine A plus B is equal to the sine of A cos B plus the cos of A sine B, and sine A minus B. This is equal to the sine of A cos B minus the cos of A sine B. Notice that these two identities are almost the same except for the sign in the middle. One is positive and the other one is negative, because one has positive angles and the other one has negative angles. If you add these two identities, on the left side of the equal sign, you will have sine of a plus b plus the sine of a minus b. And that will equal to 2 times the sine of a cos b. We will call this equation number 1. Let us make the angles a plus b equal to the small letter x. And we'll make the angles a minus b equal to the small letter y. And now we want to add and subtract these. If you add a plus b equals x and a minus b equals y, you get 2a equals x plus y, and a, therefore, would be brackets x plus y divided by 2. Now we will subtract those two identities up at the top. And when we subtract them, we end up with 2 angle b. And that'll be equal to small x minus y, and capital B equals, therefore, bracket x minus y divided by 2. These lines are all about angles. If we substitute this information in line 1, then the identity is the result, which is sine x plus sine y is equal to 2 times the sine of the sum of x and y divided by 2 multiplied by cos times the difference of x minus y divided by 2. That, therefore, solves the identity that we started out to prove. The next group of identities is called the double angle identities. By double angle, I mean if an angle is 20 degrees, then double the angle is 40 degrees. If the given angle is 30 degrees, then double 30 degrees is 60 degrees, and so on. If the angle is x degrees, then double x degrees is 2x degrees. So examining the primary trig ratios, sine, cos, and tangent, we have, as you see on the screen, sine 2x, cos 2x, and tan 2x. We begin with sine 2x. Now, recall in your study of the trig identities involving the sum and difference of angles, recall that the sine of a plus b is equal to the sine of a cos b plus cos a sine b. Now, in this example, where we have sine 2x, which is equal to sine x plus x. So if x plus x is the a plus b in the former identity, you end up with sine 2x equal to sine x cos x plus cos x sine x. Those two terms are the same. And if you add them, of course, you end up with sine 2 sine x cos x. So we come up with this identity that sine 2x is equal to 2 sine x cos x. An identity that is very often used. The next one we want to look at is the cos of 2x. Now, if you go back to your sum and difference of angles identity, the cos of A plus B is equal to cos A cos B minus sine A sine B. Now, if A and B become AX plus X, you find that cos X plus X is equal to cos X minus sine X sine X. When you simplify that, you end up with cos squared X minus sine squared X. Now, we are going to examine the other identities that are similar to cos 2x. That is, that cos 2x also equals 1 minus 2 sine squared x. Let's prove this identity. What we end up doing is, if we go back to the Pythagorean group of identities, we wrote the identity that the sine squared plus cos squared is equal to 1. So now we have a 1 in the line that says cos 2x equals 1 minus 2 sine squared x. Well, how did that 1 get there? Well, just as I said earlier, that we have in the list of Pythagorean identities that the sine squared of x plus the cos squared of x is equal to 1. How can we use that? Well, if we take this line where we have just above this one that the cos squared x minus sine squared x is equal to cos 2x, we're going to add a line to this where the sum of the two terms adds equal to 0. The two terms are plus sine squared x minus sine squared x. When you add these two terms up, that equals 0. You can see that I have added that line to a line cos squared x minus sine squared x. Now we're going to rearrange those terms. If we rearrange the terms so that I have cos squared x plus sine squared x followed by minus sine squared x, again minus sine squared x, you can see that sine squared x plus cos squared x down below there is equal to 1. So we have sine squared x plus cos squared x minus 2 squared x minus sine squared x. So sine squared x plus cos squared x is 1 minus sine squared x minus sine squared x is 2 sine squared x. When you simplify this line, you end up with the line and the identity that we were seeking. Cos 2x is also equal to 1 minus 2 sine squared x. And so what you might want to do is try to prove the identity that sine 2x is also equal to 2 cos squared x minus 1 in the same way. The final example we have is that the tan of 2x is equal to tan x plus x, and that is equal to tan x plus tan x divided by 1 minus tan x, and that simplifies to 2 tan x divided by 1 minus tan squared x. This is the last of the set of trigonometric identities you will need to progress forward. Pause the video and study the list and copy them in your journal. I will prove the first one at the top of the list, which is sine of the angle x divided by 2. That's a half angle. That's why we call this list the half angle identities. This is equal to plus or minus the square root of 1 minus x divided by 2. You should use my example proof and apply something similar to prove the rest of them. Now go to the right-hand bottom of the screen where I say to prove number 1, begin with. What we are beginning with is the identity we studied earlier. Cos 2x is equal to 1 minus 2 sine squared x. Rearrange the terms so that you have 2 sine squared x on the left-hand side, and you have on the right-hand side equal to 1 minus cos 2x. Now look at the x in 2 sine squared x. I'm going to replace the x with the half angle x over 2. So it now reads sine x over 2. I will take the 2 on the left where it says 2 sine x over 2 and divide both sides by 2. When I divide the right by 2, I end up with 1 minus cos x divided by 2. And now take the square root of both sides and I end up with plus or minus the square root of 1 minus cos x all over 2. Notice that cos 2x became cos x. Well, that's because we took half the angle when we replaced x originally by x divided by 2. So when x divided by 2 in sine x over 2, the cos 2x became cos x.